Welcome back to our next short video in this session regarding statistical significance of information measures and how to compute that in JIDT. That latter part, how to compute it in JIDT, is the focus of this short video. To see how to do this, it's very simple to do so using the GUI Auto Analyzer. All you need to do is click the checkbox next to the Add Statistical Significance phrase. The computation of statistical significance is available on all mutual information, conditional mutual information calculators and calculators based on those, like the transfer entropy. Let's have a quick look at what it looks like when you tick that checkbox. So I'll go in and I'll start the auto analyzer here. I'm going to grab an ordinary mutual information calculator. Let's do a discrete calculation. We'll do it on two coupled binary columns. Okay, if we ordinarily compute our result, we get the simple calculation here of 0.0001 bits, which looks like it's probably consistent with 0, given that we've only got 1,000 samples. But let's check that. Let's tick our box to add the statistical significance calculation. We'll generate our code again and compute, and now we see here more information on the null distribution and a p-value for our result. There is also some new lines of code here. Let's flick back to the slides to look at these in some more detail. Okay, so having run the computation, we can see then that our method gets significance on the calculator. That's what we can see in code here, is what we've called. You supply a number of surrogate calculations to compute there. The auto analyzer automatically supplies 100. You can change that number when you take these code templates and extend them yourself, and I would advise you to do so to get a more accurate representation of the surrogate distribution. That then returns what we call an empirical measurement distribution object. You can see more details on that class in the Java docs. What's important from our perspective is that it allows you to retrieve the full surrogate distribution, the mean, the standard deviation of it, and a p-value of our statistic. And that's what's represented in the print line here, and then printed out for you on the console. We can see that we get now not only the value of the result itself, but also the mean of the null distribution, the standard deviation of it, and then the p-value here. So in this calculation that's represented on the screen, we can see the p-value for our surrogates as compared to the p-value for our statistic, whether or not the surrogates were greater than or equal to it, was a value of 0.73. So that's clearly not significant. Now the surrogates are of course computed stochastically. So the value we see for the p-value here, 0.73, was different to the value that we looked at when I just ran the GUI myself for you, which I think was about 0.6 or so. Now for some estimators, we actually have an analytic representation of the surrogate distribution, which I think is quite interesting. Specifically, for the linear Gaussian estimator, for continuous value data, or for the discrete plug-in estimator, we know that 2 times the number of samples times the mutual information statistic follows a chi-squared distribution in NATS. And this is with the following degrees of freedom, which are different between both types of estimators and between mutual information and conditional mutual information computations. Interestingly though, there's no difference between the MI and the CMI null distribution for the linear Gaussian model. Here, in the maths that I've shown you, the dimensionality of x and y, dim(x) and y, simply means the number of dimensions in each of those multivariates. So as our variables become higher and higher dimensional, we get more of a spread in our surrogate distribution. Similarly, with the discrete plug-in estimator, what I'm showing, this symbolization I'm showing here means the alphabet size of our discrete variable x. So similar to what we saw with the number of dimensions increasing for x and y for the Gaussian model, for the discrete plug-in calculator, the larger the alphabet size, the more the spread in our surrogate distribution. And that makes sense because as those dimensions or alphabet size go up, it's harder to sample that state space properly, so we get more of a spread of what is consistent with a zero measurement. Finally, you'll note that I said that these distributions are in NAT. Now that makes sense for the linear Gaussian estimator. It doesn't make so much sense for the plug-in estimator because we're normally returning bits for that, but I'll take care of that under the hood for you. So when you see those results for the mean and the standard deviation of the surrogates for the discrete estimator, they've been converted back to bits for you. So you don't have to worry about the fact that the analytic results are in nats. So we can do this with the analytical statistical significance in JIDT. What's important is it's far, far faster than doing this empirically when we have it available. To do it, all we need to do is click the checkbox next to Analytic when it appears. So this option will only be available to you for the discrete calculator and for the Gaussian model. It won't be available for the KSG estimator at this point in time, although we are working on what that null distribution should look like analytically, and it may be available in future. Let's have a quick look at that in the toolkit. So coming back here, all I do now is I click the box next to analytically to compute the statistical significance. I'll run the code again, and we see now a slight difference in both our result and our code. We've now got an analytic measurement distribution object returned, and we can see here we get a p-value returned directly from that. Okay, so looking at those in some more detail, we can see in the code that we get that analytic measurement distribution object. You can see more details about that in the Java docs if you like. From that, you can retrieve the p-value of the statistic, and you can convert directly between estimates and p-values, although that's not shown directly on the screen here. The results, as I say, are a little bit more simple now. We can go straight to the p-value of our estimate. Okay, so the big pro about computing the statistical significance analytically is that it is far, far faster than the empirical calculation. And that is very, very useful when you have a lot of calculations to make. On the downside, it's only completely correct asymptotically. And you can read more about that in the Barnett and Bossemeyer paper that I referenced on the previous slides. Now, we only really care about the statistical significance, about the distribution itself when n is finite. So, obviously we'd like that to be correct for smaller n as well. So it can be significantly away from the empirical values we would generate from resampling, in particular when our distributions under analysis are highly multivariate, which increases the undersampling effects, or when the distributions on the variables for discrete data are heavily skewed. Okay, so the analytic distribution is very, very good, but it's not perfect. And if you want an estimate as good as you can get on that null distribution, you really do need to go. You really do need to go to the resampled empirical calculations for it. So you've got that trade-off there between computation time and precise accuracy to bear in mind. Coming up, we're going to further this discussion on statistical significance by thinking about undersampling and how we can use heuristics to decide, for example, how many discrete levels we may be able to discretize our data into if we are going to use a binned estimator, for example.